Welcome to the Explainer. Today, we're digging into something that sounds simple but is actually, well, incredibly complex. How do we measure distances on our own planet? It turns out there's a dilemma at the heart of it that professionals have to solve every single day. So let's just jump right in with a real head scratcher. Picture this. You take two insanely precise pieces of equipment, a satellite system and a ground-based laser, and you measure the very same line. But you get two different numbers. So what's the deal? Is your gear broken? Nope. Something much more interesting is going on. See, this isn't about an equipment failure at all. It's a fundamental clash between two completely different ways of looking at the world. The satellite, that's giving you an indirect measurement from way up in space using a perfect global model. But the laser on the ground, that's giving you a direct, real-world measurement right there on the surface. To figure out why they don't agree, we've got to track down two hidden culprits. Okay. Our first culprit has everything to do with the actual ground we're standing on and the huge gap between reality and mathematical perfection. Here's the heart of the problem. We live and we build and we measure on a messy, bumpy planet, right? Full of mountains, hills, and valleys. But for all the official math and mapping to work on a global scale, all of our measurements have to be calculated on a perfectly smooth, idealized version of the Earth. It's a mathematical model called an ellipsoid. So how do surveyors bridge that gap between the real world and the perfect model? Well, it's a clever correction process. They start with the actual distance they measured on the ground. Then, to make it compatible with the global model, they have to apply a special correction for elevation. It's called the elevation factor, which mathematically projects that ground measurement down onto the smooth ellipsoid surface. And check this out, this is what it actually looks like in practice. If you measure a 100-meter line right at sea level, well, it's still 100 meters on the ellipsoid. Makes sense. But take that exact same 100-meter line and measure it way up at 3,000 meters, and when you project it down, it mathematically shrinks by almost 5 centimeters. The higher you go, the bigger that difference gets. All right, so we fixed the elevation issue, right? We've brought our measurement down to that perfect, smooth ellipsoid. But here's the kicker. Solving one problem creates a whole new one. And this one's an age-old challenge. You just can't make a perfect flat map of a round world. You know, there's a fantastic analogy for this. Just imagine trying to flatten out an orange peel. No matter what you do, you can't get it to lie perfectly flat without it stretching or wrinkling or even tearing. Well, the curved surface of the Earth is exactly the same way. It's just a fundamental rule of geometry. You can't take a curved surface and make it flat without distorting it somehow. To put the curved ellipsoid onto a flat map grid, you're forced to either stretch some areas or squish others. And of course, surveyors have a super precise way to calculate this. They call it the scale factor. It's basically a number that tells you exactly how much distortion, either stretching or shrinking, is happening at any specific spot on your map, compared to the true distance on the ellipsoid. So what does that look like? Well, on a standard map grid, like the one used in Nepal, a true 100-meter line from the ellipsoid actually shows up as being a little shorter, 99.99 meters, right at the center line of the map. But as you move out toward the edges of the map, that same line gets stretched and shows up as being longer than 100 meters. The big takeaway here is that the distortion is different everywhere you look. Okay, let's recap. We've got our two culprits. First, the elevation problem, which squishes our measurements when we project them down. And second, the map distortion problem, which stretches or squishes them again. Now that we've identified them both, we can finally reveal the solution to our original mystery. And this, right here, is the crucial point. You can't just fix one problem and then the other. It doesn't work. To get your real-world on-the-ground measurement to perfectly match the coordinate you get from a satellite map, you have to account for both of these effects, elevation and distortion, at the exact same time. The solution is actually beautiful in its simplicity. Surveyors just multiply the elevation factor by the scale factor, and that gives them one single all-in-one correction that they call the combined factor. That's the magic key that makes the messy real world agree with the perfect flat map. And if you're thinking this is all just a tiny little rounding error, think again. If you were to just ignore this factor, a single 1-kilometer line measured at an elevation of 2,000 meters would be off by a massive 41 centimeters. That's over a foot. So, okay, a few centimeters here, a foot there. Why does this level of precision really matter? Well, out in the real world, the stakes are unbelievably high. This isn't just some academic thought experiment. An error like this could be the difference between your property line being in the right place or being in your neighbor's yard. It can mean a bridge that doesn't quite line up, a tunnel that misses its target, or a high voltage power line that can't connect. Especially in mountainous countries like Nepal, where elevations are all over the place, getting this right is absolutely critical. So, when you boil it all down, the combined factor is basically the Rosetta Stone of modern surveying. It's the key that allows professionals to take super fast modern satellite data and confidently blend it with classic, boots on the ground laser measurements. It ensures that everything and everyone is speaking the same language, saving time, money, and preventing some really, really costly mistakes. This entire problem exists simply because our measurement tools became more precise than our old methods could handle. It really makes you wonder what's next, right? As our technology gets even more unbelievably accurate, what new hidden complexities are we going to find? And how will our fundamental models of the world have to evolve just to keep up?